Oh, good day. Welcome to tutorials on differential equation, ordinary differential equations. I am Aditya Manuel. In this tutorial, we are looking at ordinary differential equation of the first order. Ordinary differential equation of the first order. By now, we should know, or we should have learned, we should have understood what we meant by ordinary differential equation and first order. So let's go straight to point. Ordinary differential equation of the first order has a general form of f of x y the y dx equals 0. It means that it's a function of x, y, and the y dx, then equated to 0. This is called the general form of an ordinary differential equation of the first order. First order, that is the y dx. Let's look at the standard form of an ordinary differential equation. An ordinary differential equation has a standard form of dy dx equals f of xy. dy dx equals f of xy. This is the standard form. So let's look at certain questions. Write the differential equation xy prime minus y squared equals 0, which is in a general form in standard form. We are requested to write this ordinary differential equation, which is already in the general form in standard form. In other words, make y prime the subject. Xy prime equals y squared. So y prime equals y squared on x. The standard form is given by f of xy equals y squared on x. This is very simple. Let's look at another example. Write the differential equation exponential x y prime plus exponential 2x y equals sine x. Express this in the general form as well as the standard form. Write the differential equation exponential x y prime plus exponential 2xy sine x in general form as well as the standard form. The general form, not far-fetched from here. All we have to do is to bring this sine x to the other side of the equation and equate to 0. Ex y prime plus exponential 2xy minus sine x equals 0. This is the general form. To the standard form, make y prime the subject of the formula. Exponential x y prime equals sine x minus exponential 2x y. Divide both sides by exponential x. We have y prime equals exponential minus x sine x minus exponential x y. F of xy equals exponential minus x sine x minus exponential x y. This is the standard form. It's very simple. Let's check another example. Write the differential equation y prime plus y all to power 5 equals sine y prime on x. Write differential equation this in standard form. To write in standard form, we are just to do one thing: make y prime the subject. Y prime is the same thing as the y dx, so make y prime the subject. There's no way we can solve this algebraically. So since we cannot get a value for y prime, we conclude that this differential equation cannot be expressed in the standard form. We conclude that since y prime cannot be solved algebraically, the equation cannot be written in standard form. That's all for now about the standard form and the general form of an ordinary differential equation of the first order. Let's check the differential form. The differential form of an ordinary differential equation of the first order is given by m, a function of x and y, dx, plus n, also a function of x and y, the y, equals 0. And we must have seen several equations like this before in the previous tutorials. You have to know the differential form. It will be very important. We're going to need it in subsequent tutorials. Let's look at this question together. Write the differential equation y prime minus 1 equals x in differential form. Write the differential equation y to bracket y prime minus 1 equals x in differential form. So the first thing, expand the bracket. So y squared y prime minus y equals x. Take this, the y to the other side of the equation, or bring x here. Anyone would do. Y squared y prime equals x plus y. Y squared y prime is the same as y squared the y dx. Y squared the y dx equals x plus y. So take this dx to this side. We have y squared the y equals x plus y dx. And let's take this to the other side of the equation. We have x plus y dx minus y squared dy equals 0. So this is the differential form of the differential equation. Don't forget that the differential form is of the form mxy dx plus nxy dy equals 0, where our mxy from the equation above is x plus y, and our nxy is what? Minus y squared. So this is the differential form of an ordinary differential equation of the first order. This is the differential form of the ordinary differential equation of the first order. Now very soon we are going to check general and particular solution of first order ordinary differential equation. How do we solve an ordinary differential equation of the first order? We have looked at how to check whether a particular function is the solution or not of a given differential equation, ordinary differential equation. We've checked with subsidiary conditions. We checked with initial value conditions, the boundary value conditions. If you are given a differential equation, ordinary differential equation of the first order, how do you go about solving it? So that's the next one to check now. Don't forget, at the end of this tutorial, I'll leave us some questions to tackle. There are several methods for solving ordinary differential equation of the first order, because the ordinary differential equation of the first order could take several forms. So the kind of forms it takes determines the appropriate method to apply. we want to start with one of the commonest method, and that is method of separation of variables. When do you say particular ordinary differential equation is variable separable? When do you say that? Now, given an ordinary differential equation of the first order, if our dy dx, or in our standard form, if we can express it in terms of the product of functions of x and functions of y, then we say it is variable separable. We understand this better with the aid of this example. Solve the differential equation x plus 1 dy dx equals x to bracket y squared plus 1. Now, looking at this, you have to ask yourself, is it possible for me to get all the values of x to one side and all the values of y to one side, all the functions containing x terms to one side and all the functions containing y terms to one side? If this is possible, then we say it is variable separable. There are procedures for solving this. So let's try this. If I bring this one here, I have the y dx equals x on x plus 1, then y squared plus 1. Can you see we have been able to separate them? So I conclude by saying that the equation is variable separable. But it's not over yet. I bring the x to where we have the families of x, and I bring the values of y to where I have the y. So you bring values of x to meet the x and values of y to meet the y. Here we have 1 over y squared plus 1 dy equals x over x plus 1 dx. Hope this is taken. I've been able to bring the values of x together to meet dx and the values of y together to meet the y. This is just a simple simplification. I hope this is not difficult. So next thing you do is, after separating the variables, getting them to meet the derivatives, then you integrate both sides. So integrate both sides. If you have problem integrating this, check my tutorials on basic mathematics for tertiary institution students. Let me integrate this. You have tan inverse of y equals for you to be able to integrate this, you need to simplify this. These and these are of the same power. So this is an improper fraction. So a simple method, you can express x in terms of x plus 1 as x plus 1 minus 1. Hope this is taken. All over x plus 1 dx, which gives us x plus 1 over x plus 1 minus 1 over x plus 1 all dx. This is what we have here. Okay, So this one gives us 1. So we have tan inverse of y equals integral 1 minus 1 over x plus 1 dx. When you integrate 1 respect to x, you have x. When you integrate 1 over x plus 1 dx, you have ln x plus 1. So you had your constant of integration to the side of the equation where you have the independent variable. You cannot have two constants on the same line and will be on the path on the side of the independent variable. Please take note of this. Most times the constant of integration is always on the side of the independent variable, and in this case it is x. So this is a solution. Looks strange, but this is a solution. You can make y the subject by taking tan of the whole equation. Let's look at another example. Solve the differential equation the y dx equals x squared on y 1 plus x cubed. We have to solve this. Can you see clearly that it's separable? This is the same as 1 on y times x squared 1 plus x cubed. So it can be separated. So now you shift sides. If you take y to this side, you have y dy equals x squared 1 plus x cubed dx. Having separated them, the next method is integrate both sides. This is the procedure for variable separable. When you integrate y dy, you have y squared on 2. Hope that's not difficult. Okay, let's just check a basic integration. If you integrate x dx, it gives us x 1 plus 1 over 1 plus 1 plus c. From basic tutorials, you can get this. This is x squared on 2 plus c. So when you integrate y dy, you're going to have y squared on 2, which is taken. And let's continue with the question. When you integrate y, you get y squared on 2 equals, when you integrate x squared over 1 plus x cubed, you have 1 over 3 ln 1 plus x cubed plus c. Multiply through by 2, you have y squared equals 2 on 3 ln 1 plus x cubed plus c. The absolute value is to help us eliminate the possibility of having negative values for 1 plus x cubed. This is taken. Ln of a negative value is undefined. So whatsoever the value of 1 plus x cubed is, we are looking at the absolute value of it, then find the ln of that. Ln is the same thing as log to base e. Please take note of this. So 2c. So we have y squared equals 2 on 3 ln 1 plus x cubed plus c. C is an arbitrary constant, so 2 times c is still the same thing as c, or let's call it c1. So from here, the solution of that differential equation y equals plus or minus the square root of 2 on 3 ln 1 plus x cubed plus c1. This is the solution of the given ordinary differential equation of the first order. Let's look at another example. Solve the equation 1 plus x squared minus x into bracket 1 plus 2y y prime equals 0. It's left to you to look at the best method you can use to separate them now that you know what to do. But we have a subsidiary condition, an initial condition here. So this is called what? Initial value problem, because of these initial conditions. Please don't forget, all these terms are very important. Okay, let's solve this. Take this to the other side of the equation. You have minus x 1 plus 2y y prime equals minus 1 plus x squared. So this cancels out. So we can take this x to this side. So we're having 1 plus 2y y prime equals 1 plus x squared on x. 1 plus 2y y prime is the same thing as the y dx. 1 plus x squared on x. Any question? Yes, no question. Then we have 1 plus 2y the y into 1 over x plus x dx. We have been able to successfully separate them. What's the next thing to do? Integrate both sides. When you integrate one with respect to y, you have y plus this will give you 2y squared on 2. When you integrate y, you have y squared on 2. The constant will not be on this side, it will be on x side because x is the independent variable. Here we have integral of 1 over x with respect to s gives us ln x. The integral of x gives us x squared on 2, then plus c. Here we have a y plus y squared equals ln x plus x squared on 2 plus c. Is this all? No. We're given an initial condition. And what is the essence of an initial condition? It's for us to get the value for the arbitrary constant c. So let's apply the initial condition. The initial condition is y equals 0 when x equals 1. Y equals 0 when x equals 1. So we have 0 plus 0 squared equals ln 1 plus 1 squared on 2 plus c. Ln 1 is the same thing as 0. So we have 0 equals 1 over 2 plus c. So c equals negative 1 over 2. So we introduce this back into the main equation, and this gives us y plus y squared equals ln x plus x squared on 2 minus 1 over 2. Can you see clearly here we cannot make y the subject? So it's better to make c the subject. If you cannot make y the subject, then let's make the constant the subject. But this is the solution already. So making this the subject, we have ln x plus x squared on 2 minus y squared equals 1 over 2. It's like the most basic level you can put this. So this is the particular solution for the ordinary differential equation of the first order that was given to us. Hope this is well understood. Don't forget we are looking at how to solve ordinary differential equation of the first order, and the method we are looking at here is the method of separation of variables. Find a particular solution. Find the particular solution of the y dx equals x squared 1 plus y squared with this condition, so just cross multiply. 1 plus y squared the y equals x squared dx. So they are separated already. What's the next step? You integrate both sides. When we integrate the y, we have y. When you integrate y squared, you have a y cubed on 3 equals x cubed on 3 plus c. If you have problem understanding this, please check tutorials Basic Mathematics for Tertiary Institution students. It's going to go a long way in helping us. Using the initial condition to get the value of our constant c, our y equals 1 when x equals 2 from this. So we have 1 plus 1 cubed on 3 equals 2 cubed on 3 plus c. We have 4 on 3 equals 8 on 3 plus c. 4 on 3 minus 8 on 3 equals c. So c here equals minus 4 on 3. So let's obtain the particular solution by introducing the value of c into the main equation. Doing that, we have y plus y cubed on 3 equals x cubed on 3 minus 4 on 3. Let's multiply through by 3 to make it simplified. 3y plus y cubed equals x cubed minus 4. And since we cannot make y the subject here, let's make the constant c the subject. So what do we have? X cubed minus 3y minus y cubed equals 4. This is a particular solution for the ordinary differential equation of the first order. Thank you. Let me give you some questions to play with, to tackle. They are not difficult, and they should not be difficult for you to solve. Exercise: solve the differential equations. Solve the differential equations. 1. 9y prime plus 4x equals 0. 2. X cos x dx plus 1 minus 6y squared dy equals 0, with the condition y pi equals 0. 3. Xy prime plus y equals 0, y of 1 equals 1 as a condition. 4. dr dt equals minus 4 rt. The condition: when t equals 0, r equals r naught. And the fifth question: xy squared dx is the fifth question, plus exponential x dy equals 0. When x approaches infinity, y equals half. This has brought us to the end of another tutorial. Please join me in the next tutorial as we check another method. Thank you.